you're live, are you going to record?
Yeah, that's recording it.
Okay.
So this goes into college algebra. Yeah, so the reason I do live is because instead of just straight recording is because it automatically goes into that YouTube playlist. So I don't have to do a second, like I don't have to save it and then upload it, where live automatically does that for me. So it's recording as we're doing the live. And that's how YouTube works anyway. So any live recording is really, any live like thing, live video is actually recording at the same time.
Yeah, that's nice. At least you know that shortcut.
Yeah. I have shared that as well, and it doesn't take up space on these laptops, which are not the best laptops. Anyway, so let's get started. So first off, we are back. We're starting a new real section, a few sections before we get to the next test. Today we're going to go over 3.1, which really is an introduction to all the different types of functions we're about to hit. If I was going to make this book, I probably wouldn't make it this way, but it's not a bad section to get a little bit of an introduction. I'm going to focus on the topics in this section that are really going to help us coming through section 3.4. I think section 3.3 and 3, I think it's 3.3 in this book. 3.3 and 3.4 are 3.3 and 3.4 are kind of the capstone, you might say, for college algebra, especially if you're looking at going on to a calculus class, but they are kind of the capstone for college algebra topics. And 3.1 is a little bit of an introduction. So 3.1 is on. What did I do? Oh, I dropped it, didn't I? 3.1 is on the quadratic function. Okay, the quadratic function. And there's two ways to write the quadratic function. One of them you've probably typically seen. That's the most common. The other is the one I'm going to start with, actually. But before we even start with the equations or how they're written, let's start with how they look on a graph. So quadratics are always either smiling or frowning. That's the best way to think of it. So let's look at one that's turned up. Okay. Let's say we've got a quadratic and it looks like this. They all kind of look like this, right? They're either going to go up or they're going to go down. And I just call it this one smiling. It's my goofy way of remembering it. Smiling or frowning. So one thing that's true, or there's a few things that are always true with quadratic and really the terminology. So quadratic's always either going to have a minimum or a maximum. And it's relative and it's actually absolute. But for this one, we've got this relative or maximum or minimum, right? We've got this minimum right here. That point where increasing, it either changes from increasing to decreasing or decreasing to increasing is called the vertex. So that point is called the vertex. And that's really a quadratic term. If it was any other kind of function, say it like came back down, up and down, we would just call them minimum or maximums. But for quadratics, they get this fancy vertex term. Now, the vertical line that goes through a vertex, and I'll just kind of make it in a dashed way. Your book finds this line important. Some authors do, and he gives it the term axis of symmetry. Sometimes you'll hear the word here called line of symmetry, but he uses the terminology axis of symmetry. And it's always just the vertical line that goes through the vertex, okay? And really, why it's called axis of symmetry is a quadratic's always going to be symmetric around that line, even if it is upside down. It's always symmetric around that line. Yeah, vertex, yeah, no big deal. So again, this could be flipped over. You're still going to have an axis of symmetry. and it's still considered a vertex. Now this vertex is a minimum, where the previous, if we flipped it over, that vertex would be a maximum. So let's look at the first form. Your book calls this standard form. Standard form of a quadratic. Okay, standard form of a quadratic looks like this. We've got f of x. Now I'm just going to put letters up here and then we'll fill it in with an example. We got f of x equals a times x minus, is it k or h? Actually, it's h. X minus h squared plus k. Okay, so f of x equals a parentheses x minus x h close the parentheses squared plus k. Now, each one of these letters are going to tell us something about this graph. Okay, they tell us something about the graph. The A actually tells us if it's pointed up, if it's smiling, or if it's frowning. So I'm going to kind of just write this out. If A is positive, I should spell positive correctly. If A is positive, if A is positive, it turns out it makes the vertex a minimum. If A is positive, the vertex is a minimum. So what that does is it means we've got this up and up behavior in behavior, okay? Well, if the A is positive, we got this up and up in behavior, and it makes the vertex a minimum. If A is negative, we've got the opposite. If the A is negative, it turns out it flips this, flips it over. And if you remember in the transformation section, if we had a negative out front of in front of the function, it made it reflect over the x-axis. That's really what's going on here too. So if A is negative, the vertex is now max. The vertex is max. That's what the A tells us. So the A tells us if the vertex is a minimum or a maximum. And really kind of tells us if the graph is smiling or if it's frowning. Okay? The H and the K here are actually our vertex. So we'll put that down. So the vertex actually is HK. Now we know this from the transformation section. Because remember, if we had subtraction inside the function, it moved the vertex kind of the opposite, right? If it was minus H, we moved it H values to the right. If it was plus H, we moved it H values to the left. And then a number out here made it go up or down. Okay, that was that transformation section. So let's look at an example of this and we'll kind of draw it over here. So let's say we had g of x equals, let's say just a is 1 for now, okay? So x minus 2 squared, let's say minus 3. X minus 2 squared minus 3. This is something that would be in this standard form of a quadratic. You can write of a quadratic too over there. So standard form of a quadratic. So g of x equals x minus 2 squared minus 3. Now, I'm going to write this down, but you'll have to. The a is just a 1. So that tells me my vertex is now 1 is positive, right? A is 1, so vertex is going to be a minimum. It tells me about my vertex is going to be a minimum. I'm going to kind of sketch this one over on the side here, okay? Well, what's my vertex? My vertex actually, now look, it's going to be minus 2 on the inside, so that means it goes 2 to the right. And notice it's minus h, so therefore it's a positive 2. So my x value of my vertex is going to be positive 2, but my y value is going to be minus 3. That's my h and my k, okay? My h and my k. So if I did a rough sketch of this, super rough sketch, not perfect by any means. Let's do my okay. We know that the vertex is 2, negative 3, so over 2, down 3. And we know that that vertex is a minimum, so this is actually going to be going up, right? Now, I'm going to find some other coordinates on this just for for graphing purposes. But the next part, let's talk about that axis of symmetry. Axis of symmetry. Remember, the axis of symmetry is the vertical line that goes through this vertex. Now, vertical lines are always x equals a number, right? And our x value of this vertex is 2. So if I ask you, or if the test asks you, or the homework, for the axis of symmetry, it's always kind of nice and easy to find. It's just x equals whatever the x value of the vertex is. So there's this nice line of symmetry right here. I'm going to just do a dash line because we don't really graph it. It's just there, but we don't really see it. Okay, just for some graphing purposes, I'm going to find the y-intercept just to see if I can get this to look a little, look nice. Okay, if I wanted to find the y-intercept, we'll find x-intercepts here in a minute. But if I wanted to find the y-intercept, remember you just set x equal to 0. So if I go to this function, I'm just going to set, now it's hard to kind of write down here. I'm going to set x equal to 0. And I would get 0 minus 2 squared minus 3. So I'd get, now 0 minus 2 is negative 2. But when you square it, it becomes positive. So 4 minus 3, you wind up with 1. So my y-intercept turns out to be 0, 1. So I'm going to graph that. I'm going to graph that on here. My y-intercept, so remember that's where we cross the y-axis, is 0, 1. It's right there. Now, what the line of symmetry tells us is we have another coordinate. If that's a coordinate on this side of the line, symmetrically, there's got to be another coordinate in the same spot, right? So look, from the middle, if we go over 2 up 1 over 2 up 1, there's going to be another point about right there. So that just gives me a better idea of how this quadratic looks. Okay, it's not perfect. And we'll find more details about this quadratic. Maybe not this one, but one here in a little bit. We'll pull a lot of stuff off. Okay. Boom, we've got this graph. Now, this all comes from this standard form of the line, right? We know that the A is positive, so it's going to be pointed up, right? It's going to be smiling. It's symmetric around, or the vertex though has to be 2, negative 3, because it's a minus 2. It's got to go to the right 2 and then down 3. Axis of symmetry just goes through, the x coordinate of the vertex. And then we found the y-intercept. Now, let's find 2 more things, okay, for this one. Let's just find the domain and the range. Just for funsies, okay? Not really for funsies. We'll see a pattern here with quadratics and their domains and their ranges. Okay, now remember, domain is where the x values exist. It's how far to the left do the x values go and how far to the right do the x values go. Okay, and if you look at this graph, this x, the x's, they go, since there's an arrow here, right? They go forever to the left and forever to the right. And if you remember from section, gosh, it's been a while, 2.6, we talked about there being 2 red flags for the domain, right? I gotta make sure to put the right finger down here. The first red flag was x's in denominators. Well, this does not have an x in the denominator. The second red flag, you guys remember it? Brownie points on who can remember. The second red flag for domain of any function. I'm going to wait until somebody guesses. You can just yell over people on the Zoom. It's fine. What was it? What was it that caused the goofiness? Remember, we couldn't have an x in the denominator because it might wind up being undefined, right? The x value could cause an undefined. What was the other thing that could happen that could mess it up? I called it glitches, maybe even.
It had a negative somewhere.
Yeah. It's scary. It's really loud on our side, but you're fine. I need to wake up. It did have to do with negatives, but where were the negatives?
Probably in the front. I'm sorry, it's early.
That's fine. I mean, this is why I need your brain juices to be flowing a little.
Was it like in a square root?
Ooh, say it again.
In a square root?
In the square root, right? Even, and I'm going to expand that, Kinsey. I'm going to say even roots. Okay. So look,
Thank you.
if we had negative numbers, or really what could cause negative values under an even root? We don't have that either, though. Okay, whoop here. And I'm going to tell you a little secret. We'll never have that with quadratics. Okay, we'll never have an x in the denominator. We'll never have square roots going on. So therefore, the domain of all of these quadratics will always be negative infinity to infinity. It will always be all real numbers, okay? For quadratics. It's a good review. Okay. Now, the range, though, is not going to be, right? Because we stop, on this one, we stop going down at a certain point, right? If you look at the y's, we stop going down right here. Our vertex, actually, is our minimum. So now we're going to look at the y values, and we go down to what, -3, and then we go up forever. So -3 to infinity. That is our range. -3 to infinity. Oh, this is a good question. This has good stuff going. This is a good, like, A, B, C, D, E, F question. Okay. This is a good one. One of those. It's hitting a lot of topics, previous topics too. Any questions before I go on to another example? I'm going to stick with the standard form, but I'm going to do a different example for the quadratic here. Questions, comments, concerns?
So you don't need the x values for the 2 dots?
Oh, well, I know this x value is 0, right? Because of the y-intercept. But I'll tell you, Jeanette, for this example, no. Because it was just, I was just kind of getting a quick sketch. Does that help? But now I'll tell you, we're on the next example, I'm going to have you find the x-intercepts as well. So we'll do both. We'll find the y-intercept and x-intercept. But for this one, it was just more of a quick sketch. But I'll tell you though, if this one is 0, 1, this one has to be 2, 1. Because of symmetry, because it's symmetric right here, right? If it's 2 over to the left and 2 over to the right, I know the x values. It's got to be 0 here because it's 2 minus 2, 0. And then it's got to be 2 here because it's 2 plus 2 right there because of the symmetry, because of the symmetry. That's a good question. That's a great question, actually. Okay. Okay, let's do another one, another standard form. I'm going to ask even more questions on this one. So get ready to pull out a piece of paper and fill this one up with maybe just a single question. Okay, so let's say I'm going to go as far left as I can on the screen. Let's say we had f of x equals -2 x plus 3 squared. This is where it's got to get a little goofy here. Let's say plus 2. Okay, x, so -2, x plus 3 squared plus 2. Okay, all right. So let's just pull information off of this thing before we graph it, okay? We're going to pull information off, and then we'll do a sketch over here once we have all the information just from this equation. So first off, my a value, I'll make this part A. My a value equals -2, right? So what does that tell me about my vertex? You guys can shout it over.
Downward.
It's downward and it's going to be a maximum. That's two perfect ways to describe it. We know what this is going to look like now just from the -2, right? Just because of the A is negative. I know it's going to be frowning, and I know that makes that vertex maximum. So I would write both of those down. That's perfect. So it's going to be, you know what? I'm going to use a little terminology. It really doesn't come up till the next lecture, but I'm going to write this as that. That's what that's a visual way of saying it's going to go down and down. Okay. A notation way, I should say. It's going to go down and down. And then also it means our vertex is right underneath. Run out ink is a max. Okay. So kind of neat. That A tells us a lot about this function. So let's find the vertex now. So the vertex for this one, now look, okay, this is a little different. We've got a +3 here. And remember, it's the opposite. Remember, if we add 3 inside, it goes to the left 3. So it's going to be the opposite for the X, but it's going to be the same for the Y. So -3, +2 for this one, okay? So -3, because it's really the opposite on the inside, and +2 on the outside. Okay. So we know what it kind of looks like in general. We know it's going to be frowning when a vertex is a max. We know where the vertex is. Let's talk about the axis of symmetry. I'll tell you, if I lectured this, not out of this book, I probably wouldn't even include axis of symmetry. But because Dr. Blitzer just thinks it's important, that's why I'm going over it. Okay. Remember, it's a vertical line, so it's always x equals, and it's whatever the x value is in the vertex. So x equals -3. Okay, just from that, I'm going to kind of start my sketch over here. See if I got enough. Oh, yeah, I got plenty of room. Okay, let's see here. So -3, -3, +2. I know that's my vertex. I know I'm going to be going down. I'm going to get more specific coordinates here. So I know I'm going to be going down, but I know my line of symmetry is right here, right? Okay. I know that vertex is my max. Okay, so let's do the y-intercept again. A, B, C, D. Y-intercept. So here's a good question. Could we ever have more than one y-intercept? Could we ever have more than one y-intercept? What do you think? I got a maybe in the seated classroom.
I know, but I'm not sure.
I got a no and a maybe in the class, but I'm not sure. Right?
Maybe, I don't know, but probably not.
Would you have 2 because it'd be like mirrored on the other side of the axis of symmetry?
Okay, now you'd have a coordinate that would mirror it, but that wouldn't be a y-intercept. Like if you go back to our last example, I wish I had the graph up. You know, one of those coordinates was the y-intercept, the other one wasn't, because it didn't go through the y-axis. That's a good, I like where your brain was going though. Could we have more than one y-intercept? No one's felt confident yet on this, right? It's a good question. I know, I like bringing it up. And I'm going to underline something, and I'm going to ask you the question again. We're talking about quadratic functions. Could I have more than one y-intercept?
No, because you can't have 2 of the same y for it to be a function.
Say it again. Was that
You
Kinsey?
can't have 2 of the same points on y for it to be a function.
Yeah, you can't have 2 of the same points on a vertical line, right? Remember the vertical line test? And so we've got this vertical line built in, right, to the graph. We can't have, this thing can't, think if it did cross more than once, first off. Think if it crossed like here and here. First off, it would not look like a quadratic, right? It's not frowning. But it couldn't do that because it wouldn't be a function, right? So we'll always have a y-intercept with quadratics, but it'll always be just one coordinate. Okay, because if not going to be a function. Okay, so let's find it now. Okay. Let's find the y-intercept. So we're going to plug 0 into x. Remember, we need to plug 0 into x. So we get negative 2 times 0 plus 3 squared plus 2. Okay. Now look, guys, I'm going to be a little lazy here and zoom through this. 0 plus 3 is 3, right? You square it, you get 9. So negative 2 times 9 plus 2. Oh, God, it's going to be a really negative number. Negative 18 plus 2, that's negative 16. Okay, it's just way down here somewhere. 2, 3, 4, 5. I'm not going to graph this one. It's just really far down here, right? Because it's negative 16. So the y-intercept would be 0, negative 16. Okay, that's fine. So let's find the x-intercept on this one. Let's find the x-intercept. This should be something, this should be a review, A, B, C, D, E. Should be a review on how to solve using the square root method. Because remember, with x-intercepts, we set the y value equal to 0. So I just set this whole thing, x plus 3 squared plus 2, equal to 0. Now look, I can't distribute this negative 2. I'm going to tell you all the things that students, how they get this wrong, okay? I can't distribute this negative 2 first because of the squared. Remember, order of operations, exponents get priority. I can't distribute this 2 in. That's my number one pet peeve in all of algebra, okay? I can't distribute this 2 in because I have an addition sign. Now, if you want to FOIL it out, you can. X plus 3 times x plus 3, that's fine. There's just a much easier way to solve this one, and it's the square root method. We went over it like the first lecture this semester. It's just been a while. It snowed a lot. We've slept a lot, okay? So I'm going to go over a review on how to solve this with the square root method. The goal with the square root method was to get whatever is being squared by itself, okay? Whatever is being squared by itself. I'm going to time this mask up. So I want to stay on. So if I want to get x plus 3 squared by itself, first I've got to subtract the 2. And I get x plus negative 2 times x plus 3 squared equals negative 2. Then I've got to divide by that. I got to get that negative 2 to go away. So I'm going to divide both sides by negative 2. And I wind up with x plus 3 squared equals a positive 1. So the first step, if you go back and watch that lecture from, it was either the first lecture or the second lecture we went over in section 1.5. First step in using the square root method was isolating the squared term. The next step was taking a square root, and when you do that, you have to remember to take a plus or minus. So we do the square root of both sides, and we have to remember the plus or minus. Okay? We take the square root of both sides, right? And the goal is to get the squared to go away, right? It'll cancel. The root and the exponent will cancel. And on the left, you're left with x plus 3. But on the right, we're left with, for this example, we're left with plus or minus 1, right? The square root of 1 is just 1. So we're left with plus or minus 1. Now let's subtract 3 over, and I get x equals negative 3 plus or minus 1. And I need to solve these. Look, it's a quadratic typically gives us 2 solutions, okay? It typically does. We might do one here in a minute that gives us just 1. But I got to solve it out. I got to add the 1 and subtract the 1. So x equals negative 3 plus 1, that's a negative 2. And negative 3 minus 1, that's negative 4. And there are my 2 x-intercepts. We had to work hard for these x-intercepts, right? And typically you have to work harder for x-intercepts than you do for y-intercepts. So let's write this down. So negative 2, 0, and negative 4, 0. And we'll see these x-intercepts will naturally be symmetric around the line of symmetry. So negative 2 is right here, and negative 4 is right there. See how they're symmetric around the x-intercept. I'm sorry, the axis is symmetry, not the x-intercept. Okay, A, B, C, D, E. And if you're like, oh my God, I don't remember any of this, this is called, it's from 1.5, solving by the square root method. I should say solving quadratics. Solving quadratics by the square root method. So if you want to look back at that, or if you wanted to get on YouTube and look it up, that's what it is. Just if you want to see a few quick videos on remember how to do that. I looked at it for a student not long ago. There's a lot of good stuff out there that pops up when you search for that. Okay, so now let's kind of get an idea. We kind of have an idea now what it looks like. Something like this. Right, and we know that x-intercept's really way down here somewhere. That y-intercept, I should say, is way down there. So let's do the last two, A, B, C, D, E, F. Domain. And then the range on this one. Domain's the easiest question, right? It's going to be the same for all quadratics. There's no goofy things like that. There's no glitches, no red flags. It's always going to be negative infinity to infinity for quadratic functions. Okay. The range, though, is a little different here. The range goes down forever, right? But then it stops. It peaks because the vertex we know is a maximum. It peaks right here at what, 2? So negative infinity to positive 2. Now remember that 2 gets a bracket because we can be y equals 2, right? We can be y equals 2.
If that graph is drawn all the way down, does it touch the negative 16?
Yeah. If you keep going, Jeanette, it will eventually go through the y-axis at negative 16. Yeah, that's the y-intercept. That is the y-intercept. Okay. Any other? This is a great. Those last two were great examples of the standard form. I'm going to do an example of the other form that we're probably more familiar with when we look at it. I'm going to do another. The next example will be just. I call it the general form. I don't think your book gives it a name. But are there any questions about this one before we go on? We're going to answer the same questions. Okay, it'll just be in a different form now. Any questions? I'm going to start erasing this. Yeah. Really, and before we get to all the questions, we need to talk about how to find the vertex in the other form. It's a little different. So the other form looks like this. Let's say f of x equals, and I'm going to steal some that have nice vertexes so the math isn't that hard. Come on now. Yeah. F of x equals, let's say negative x squared minus 2x plus 1. Okay. And notice this is different. There's no parenthesis. Can you guys? It's almost on
That's the formula that it's like ax squared plus bx
Yes.
plus c.
Yeah, you're exactly right. It's on the very top of page 335.
I just want to make sure it's like the correct one.
Yeah, no problem. Yeah, the very top of page 335, it goes over the graphing quadratic functions with the equations in this form. And they don't give it a name. So I'm going to call it general form. Just so when I refer to it, you guys know what I'm talking about. So this will be the general form. Standard form is the one we did earlier. Okay. And what's more difficult out of this form is finding the vertex, because in the other form, it just gives it to us, right? I mean, it's the H and the K. So it's a little harder to find the vertex, and we're going to go over how to do that first. Okay, so how do I find the vertex in this form? Now, you guys remember the quadratic equation, or I should say quadratic formula. Remember, it was like, if we have something in this form and we wanted to solve for it, it was x equals like negative b plus or minus the square root, b squared minus 4ac, all over 2a, right? Well, the very beginning of that equation is really how you find the x value. And if you look at on the bottom of page like 334, it goes over this. But if I ask you to find the vertex, in general form, the x value, you start there actually. You find the x value first. And x it's the very beginning of that quadratic formula. Remember, it's negative b. And then it's all over 2a. That's where it comes from. So your x value will always be negative b over 2a. So if we look at our example here, our a value would be -1, right? Because it's the number in front of the x squared. Our b would be -2, and our c would be +1, the constant out there. So if I wanted to find the vertex, the x value of the vertex is always negative b over 2a. So it's going to be negative, and b is -2, over 2 times a -1. There's a lot of negatives going on. Yeah. So in the numerator, we just get a +2, and in the denominator, we get a -2. So this winds up being -1. So we found the x value for the vertex, okay? We found the x value for the vertex. Now, if we've got the x value, how do you think we need to find the y value? How could we find the y value?
Plug the x into the equation.
Exactly, Kaylee, right?
Yeah.
Kaylee said, just take the x value and plug it back into the equation. That's going to give you the y value, okay? So take the x value once you have it and plug it back into the equation, and it gives you the y value. So I'm going to take this number and plug it in as my x value, and that's going to pop out my coordinates for my vertex. So we get -1 squared -2 times -1 plus 1. So we wind up with, now, okay, let's see this first. -1 squared would be a +1, but then you make it negative. So that first term just turns out to be -1. -2 times -1, that's a +2 plus 1. So we wind up with +2. Sweet. So my vertex, just to kind of bring this back, my vertex then is the x value is -1. We worked hard to find that. And the y value, we just plugged it in to get +2. Okay, -1, 2. And I'll tell you, that a value is the same a value from the last form. So that a value, which is -1, what does that tell us about this vertex? Is it a maximum or a minimum? Say it again.
Maximum.
It's a maximum, right? That a is negative. It's the same a as the previous form. That a is negative, so therefore this is going to be a maximum. I'm not worried about that right now. We're just going to find vertexes. We're going to do probably 3 examples of finding vertexes. Okay? But I want you to know that a value is the same as that standard form. Okay, so I want you to try this next one. I'm going to steal an example from the book. It's always fun. Yeah. Use the vertex. Okay, good. This is number 14 in your book on page 343. Number 14. F of x equals 3x squared minus 12x plus 1. So I want you to try this. It says find the coordinates of the vertex for the parabolic. I haven't used that terminology, but parabola is how you would describe the shape of this graph. So if you hear the word parabolic or parabola, it just means the shape of a quadratic. But just find the coordinates of the vertex for the parabola defined by the given function. So find the vertex here. I'll give you a minute. Find the vertex. Keep working if you're working. I'm gonna try this one. So I know my x equals negative b over 2a, right? A b, okay, I'm gonna write these out. A equals 3, b equals negative 12, c equals 1, right? So negative b would be negative 12 over, my a is 3, so 2 times 3. So this becomes 12 over 6, 2, okay? X equals 2. But again, we're not done. We've got to plug it in to get the y value. So we get f of 2, 3 times 2 squared, minus 12 times 2, plus 1, right? 2 squared is 4 times 3. That's 12. Negative 12 times 2, that's negative 24, right? Am I getting the same thing you guys are getting? Did you get negative 11? I don't think that's what the book got. Oh, maybe it did. It doesn't tell me the answer. Did you guys get that?
Yeah, it's negative.
Negative 11? Okay.
Mm-hmm.
2 negative 11 is the vertex, right? Now, is this a maximum or a minimum? Why? Not the 2.
Max, it's a negative.
No, it's a minimum. Why is this a
Minimum
minimum?
because 3x.
Yeah, not the x, but the 3, right? Because
Oh.
that a value is positive, right? Yeah, 3 is positive, so this is going to be a minimum. So let's write that down. Minimum because a is positive. Minimum because a is positive. Okay, minimum because a is positive. Okay, those are 2 good examples. We'll do another one built into this next example, and we'll do the whole graphing thing again. Okay, we're going to answer all the questions that we did in the last one, but know that finding the vertex is just takes a little bit longer if it's in this general form. So let me steal one or 2. Okay, this is okay. Yeah. Let's say we were given.
I have a question before you move on, and it might just be I'm having the right part. Where do you get the negative 11 from? Other than bottom.
Okay, yeah. So 12 minus 24 is negative 12, and then plus 1 would be a
I
negative
get
1.
it the other way. Got it wrong. That's the whole time I forgot what it was.
Oh, yeah. What do you mean by the other way?
Well, I for some reason did like. I think I subtracted something different because I like negative 35, and so it was really that's why I was confused. I just confused myself with it.
Okay. Do you see how I got it there? Okay.
Thank you.
Yeah, no problem. Okay, let's look. I'm going to steal one from the book again. This is number 28 on page 343. I have no idea what this answer is going to be. So it's a nice bag here. Okay, so 28, 2x or x squared minus 2x minus 15. Okay, this is number 28 on page 343. And the question asks, use the vertex and intercepts to sketch the graph of each quadratic, give the equation of the parabola's axis of symmetry, use the graph to determine the function's domain and range. Okay, all those things I was asking you before. Okay, so let's first find the vertex. So write this down this way. I'm going to give you a minute. I want you to try to find the vertex. Try to find the vertex by yourself. Give you just
I'm
some
sorry,
minutes.
sir, but I have to leave a little bit early.
That's fine. That's fine. If you want to come back, it'll be in that folder. Was that Rose?
Yes.
Yeah. It'll be in that folder if you want to watch the rest.
Have a great day.
You too. Have a good one, Rose. Okay, so find the vertex. I'm going to follow along. You keep working and see if we get the same thing. A is going to be 1, B is negative 2, C is negative 15. So negative b 2 times a. Do you guys get 1 for the x? Plug 1 in. 1 minus 2, negative 16. You guys get that for the vertex? I got 1, negative 16. I could be right. I could be wrong.
Honestly, and trust your mathematics.
I kind of zoomed through it though. I think that's right. Negative b over 2a. Yeah, this looks right. And we'll check it. I mean, look, I'm going to check the other parts of this and we'll see if it kind of flow, if it looks right, right? This one dips real low to negative 16. Okay, let's find the other parts of this graph. Let's find the intercept. So a, b. I'll tell you the y-intercept. Oh, actually, is this going to be a max or a min? Maximum or a minimum? It's going to be a minimum because that a is positive, right? So this is going to be a minimum. Okay, so b, let's find the y-intercept. It's really easy out of this form. The y-intercept in this general form is really easy to find because remember, you just put in a 0 for x, and every term has a 0 except the constant. So if I plug 0 in, I'd get 0 squared minus 2 times 0, or 0 for 0 here, minus 15. Got to be negative 15. So that's my y-intercept. 0, negative 15. So it turns out if you're in this form, this general form, this number right here is always your y-intercept. Kind of neat, okay? So if you're in general form, that constant is your y-intercept. Now that's not true at all for that standard form. So if you have to go memorizing things. Now you need to memorize how to find it and plug in y or x equals 0, but you don't have to go through memorizing stuff if it's kind of getting mixed up when you're in the homework. Let's find the x-intercepts. A, B, C, D. No, C, not D yet. X-intercept. Now again, the x-intercept, you set the whole thing equal to 0. Hey, this is something that should look familiar. Right? That should look familiar. This is just solving quadratics. We could use the quadratic equation. We could use factoring if this thing factors, which I think it does. So I'm going to factor it. Okay? I'm going to factor it because I believe it factors. If it didn't factor, we'd have to use a quadratic equation. I'll try to get an example where we have to use a quadratic, maybe on this next one. So x squared minus 2x minus 15 equals 0. I'm going to solve it by factoring. The x squared's by, it's nice because it's by itself, right? There's no coefficient. So we could do x minus 5, x plus 3 multiplies to give me negative 15, adds to give me a negative 2. And now I set each one of those equal to 0. This is solving quadratics by factoring. So if you're like, oh my God, I'm lost, I forgot this stuff. Solving quadratics by factoring. Write that down. So add the 5 over. X equals 5. Subtract the 3 over, and x equals negative 3. Okay, so I've got two x-intercepts. 5, 0. Remember the y is 0, right? And negative 3, 0. Okay, so I've got the vertex. I've got my intercepts. I'm going to graph it from here and then get my domain and range. So this y-intercept or any of the vertex, that goes pretty low. So I'm going to take that into account when I make this graph. Okay, I'm going to go by 5s here. 5, 10, 15, 20. Okay, so I went by 5s on my digits because my minimum, or my vertex, which is my minimum, is at 1, negative 16. So about right there. There's my vertex, right? There's my vertex. And it's a minimum, it's gonna go up. Now, my y-intercept is 0, -15, so it's about right there. We didn't talk about axis to symmetry. I need to do that one. Hold on, A, B, C, D. Axis to symmetry, it's the same. It's always the x value of your vertex. X equals 1. Whatever. Now, my x-intercepts are +5 and -3. Now, -3 is about right there, right? +5. Hey, you know, these all look like they go together. I mean, if this is the minimum and we notice that parabolic shape, that U shape, looks something like this, right? It's not perfect, but that's okay. It's not perfect. But from this, I can get the domain and range A, B, C, D, E. Domain, you guessed it, all real numbers. That doesn't change for any of these. But the range, though. Let's see. It goes down to -16 on the vertex, right? And it goes up forever. So -16 to infinity. Cool. So same stuff we answered from in the last form. It's just some of these, like the vertex is going to take longer, but the y-intercept's going to be quicker, right? The x-intercepts probably take about the same, and the other 3 take about the same. So it's kind of give and take, and it's not that one is better than the other. I'll tell you, this is actually called polynomial form, and we'll talk more about that over the next 2 days, or 2 lectures, I should say. We're going to really, what your book goes into is polynomials. This whole chapter is about polynomials. So this is the form you're going to see throughout this chapter. Is this general form is what I call it, but it's really polynomial form. Okay. Questions? I'm going to give another example in this form, and I'm going to try to make one where we have to use the quadratic equation to solve it out. Okay. Questions before I erase this one? Okay. So you know what? I'm going to be a little lazy. Just do it like this. Just so I don't forget the question. Super lazy in the domain. Okay. The vertex. Okay, so let's think of a different function here. Let's say we've got negative x squared minus, let's say plus x minus 5. Hold on. Oh no, let's say plus 2x minus 5. Plus 2x minus 5. Yeah. And I want you to find, guys, I want you to do this. Find the vertex, find the y-intercept, get those 2 done, and then we'll get to the x-intercepts, okay? So find the vertex, and then tell me if that vertex is a max or min. We'll know this. It's negative, right? It's a max. So find the vertex and then find the y-intercept. I'll give you a minute to do that. And then we'll fill out the rest. Check something really fast. keep working if you're working. I'm just gonna kind of follow it up here. So x equals negative b over 2 times a, right? Negative b over 2 times a. So we get negative 2 over negative 2. So we get a positive 1, right? So I plug that 1 in and I would get negative 1 squared plus 2 times 1 minus 5. Now be careful. That negative is not being squared, okay? That negative is on the outside. The only thing that's being squared is the x. So you wind up with negative 1 there. Yeah, plus 2 minus 5. You're not the only one that fell for that. And you wind up with a, is that negative 4? Negative 1, yeah, minus 6. So the vertex we wind up with, actually I'll write it here, is 1, negative 4. Okay, we wind up with 184. And the a is negative, so it's going to be a maximum, right? 1, negative 4, and it turns out to be a maximum. Okay, now we need to find the y-intercept. Well, we just set 0 in there for the x. Oh, it's just a constant, right? Negative 5. I'm going to be lazy. Efficient is what we like to say in mathematics. I'm going to be efficient and say that these two terms go away if you put 0 in. So you're left with negative 5. So the y-intercept is 0, negative 5. Okay. Okay. Questions about that, guys, before we go to the x-intercept? Okay. So let's try to find these x-intercepts. So I'm going to set this whole thing equal to 0. Now I'll tell you, I like a positive x squared. So I'm going to do a little trick here and divide everything by negative 1. And that's purely because if we use the quadratic equation of the formula, it's easier if the a is positive. So this winds up being x squared minus 2x plus 5 equals 0. Now look, this thing does not simplify, or doesn't, I'm not simplify, or this does not factor, because 5 is only, it's 5 times 1 or negative 5 times negative 1. Neither of those add up to negative 2. So I'm going to have to use that quadratic equation. So x equals negative b plus or minus the square root b squared minus 4 times a times c all over 2 times a. Okay, so the quadratic equation we went over at the beginning of the semester, I'm going to have to use it here. Okay, now I'm going to simplify what's underneath the radical. So we get positive 2 plus or minus. Now under this radical, we get a 4 minus 20, right? So we have positive 4. Negative 4 times 5. Here, I'll write this out. 4 minus 20 all over 2. So we wind up with 2 plus or minus the square root of negative 16 over 2. Keeps going. Well, the square root of negative 16 is imaginary, right? We can't. We talked about this earlier for the domain. You can't take a negative square root, and it's not that you can't take a negative; it's that it turns it imaginary. So because it turns it imaginary, we're going to write this as 2 plus or minus 4i all over 2. Oh, which is kind of a bummer for finding x-intercepts because that x-axis is only real numbers. Okay, it's only real numbers. But I'm gonna solve this one out. I got to divide everything by 2, so we wind up with 1 plus or minus 2i. Okay, what does that mean? Right? What imaginary? He's throwing a non-real at us. Okay, let's see what that means. Let's graph what we know. Let's graph what we know. We know that the vertex is 1, negative 4, right? 1, negative 4. We know that. We know that it's a maximum. Well, think about that. I mean, the y-intercept's 0, negative 5, right? The y-intercept's right here. And we know that's a maximum. Will this ever go through the x-axis.
So you just wouldn't have an x-intercept for it then?
Bingo, right? Now, the clue algebraically is that we wind up with an I value for my x-intercepts. You didn't have to do any of this part if we would have graphed it to begin with, okay? If I would have graphed this, I could have seen, hey, this doesn't go through the x-axis. There's none, I'm gonna put none here. There's no x-intercept, okay? It doesn't go through the x-intercept. You didn't have to do all that work. Now, I wanted us to do the work so I can show you what happens, but you don't have to do all that work. If you would have graphed the vertex and realized, hey, that vertex is below the x-axis and it's the max, right? You could flip it and say the same thing. If we had a vertex above the x-axis and it was the minimum, it'll never go through the x-axis as well, okay? So we have no x-intercept. Oh, that's fine. That happens. Axis of symmetry is still just x equals 1. I think that was the same as the last one. Domain doesn't change. Range, though, now we go up to -4, right? So it's going to be negative infinity to -4. Negative infinity to -4. Questions about this one?
Is there ever gonna be a problem where the domain will be numbers rather than just infinity?
No, because you'll never have division of x's and you'll never have square roots in the original function, right? You'll never have that in the original function with a quadratic. And really what that means, what's gonna happen is you'll never have that with a polynomial either, but that kind of guides us into the next section. We'll talk about that more in the next one. The book calls it all graphs like these are smooth and continuous. And so it means, yeah, it never stops, right? Smooth and continuous. Okay, I've got 10 minutes and I'm going to squeeze in a quick example. If you have to leave before, it might go a little bit over. If you have to leave, you're not going to hurt my feelings, okay? But I want to do one more example that's just kind of goofy, but I don't think it'll take that long algebraically to cover. Let's say we had a function. Let's call it g of x. A little curveball here. G of x. Run out of ink. G of x equals x squared minus, let's say 4x plus 4. Okay. X squared minus 4x plus 4. And we're going to answer the same stuff we've been answering so far. I know I didn't do one with a fractional vertex, and it's not that I didn't want to. They're a little more challenging. They take a little more time. So just take your time once you get to fractional vertexes. Just take your time. And I don't mind going over, if you hit one of those and you just can't get the right answer in the homework, I don't mind hitting it in the next lecture.
You still just solve it the same.
Solve it the same exact way. You'll get fractions. And what's nice about your calculator, that TI-8384, it can do fractions. Just Google it. Get on YouTube and put how to do fractions in that TI-83. And you never have to worry about fractions again. Okay, so let's find the vertex. I'm going to do this one with you. So the vertex, we know the x value is going to be negative b over 2a, right? Negative b, so negative 4 over 2a. So we wind up with 4 divided by 2. So we wind up with x equals 2. Okay, so I'm going to kind of zoom through this one because I'm running out of time. I'm going to plug that into the function. So 2 squared minus 4 times 2 plus 4. So it'd be 4 minus 8 plus 4. So 4 minus 8 plus 4. Now, what's different about this one? What's weird? It turns out to be a 0. Turns out to be a 0. So here's my question. Quick question. Poll in the audience. If this is a 0, is it an x-intercept or a y-intercept? Is it the x-intercept or is it the y-intercept? You guys can yell it out on Zoom. Or you can raise your hand. If you hate yelling over people, you can raise your hand. I can see it. If you want to raise your hand and then so you don't feel like you're budging in. I know that's really annoying.
That would be at the origin, wouldn't it?
No, it wouldn't be at the origin 0, 0, right? So is 2, 0 an x-intercept or a y-intercept?
X.
Why, Jeanette? I know. Follow-up question. Why is it an x-intercept? You're on mute.
Well,
Okay.
it just seems like every time we do those, the first number is the X.
Yeah. Oh, let's go with it. Okay. Whatever is the non-zero is going to be the intercept, right? So notice this. This is our x value, right? And then we got back a 0. So therefore, that's going to be the x-intercept. It was the reverse is we plug 0 into here, right? 0 in for the x. That's how you get the y-intercept. This turns out to be our x-intercept when we get there. But let's write this down. 2, 0. It's going to be a minimum, right? Because a equals 1. So let's find the y-intercept. Remember, this is the easy way to find the y-intercept. If it's in this form, it's always just that, okay? But if you plug in g of 0, you're going to get back 4. So 0, 4, and zoom in through there. Let's kind of graph what we have. Yeah, I got to put here. I'm going to graph what we have, just in case I don't have to worry about doing x or y intercepts, right? If I would have done this before on that last example, I wouldn't have even had to find the x-intercept algebraically. So let's graph what we have. We know the vertex is 2, 0. Right there, right? And we know it's a minimum, so it's going to go up. The y-intercept's 4. 1, 2, 3, 4, boom. Okay. We don't have to find the x-intercepts again, because check this out. If that's my vertex and I go up, it looks something like this. I'm running out of ink here. Something like this. Ooh. So what this, I'm going to say this bounces off the x-axis. Okay, that's the terminology I'm going to use because we're going to talk about it more. I think it's in the next section. It might be in a section after, but it bounces off the x-axis. So what that means is we've already found the x-intercept, ABC. There's only one x-intercept for this one because it bounces, okay? It touches that 2 and it goes the other way. So the x-intercept's the same exact as the vertex. This is a very special case. Whenever your vertex is on the x-axis, it means it's also the x-intercept, right? Just a very special case. I wanted to hit ABC. What else did I ask you guys? Was it, axis of symmetry. Well, x equals 2, right? If you want to graph it, we haven't really graphed the axis of symmetry in the last few. A, B, C, D, E, the domain. Ask a question if you got a question. Just yell at me. The domain is the same as it's always been. A, B, C, D, E, F. Range. Range is a little different here, right? I mean, it goes up forever, but then it comes down to 0, to y equals 0. So it would be 0 to infinity, right? 0 to infinity. That's where the y's exist. They start at 0 and they go up to infinity. Cool. Hey, I got that. I snuck that in right before 10:40. We are good. That clock's a little fast. Okay, for homework. So 1 through 43 odd. So this is section, is it 3.1? Page, it starts on page 343. 1 through 43 odd. Now these are all going to be odd. I'm going to give you some real world examples from this section. I know we didn't have time to go over one, but I want you to attempt them. And if you have issues with them, we'll talk about those too at the beginning of class. Okay, on the next lecture. Not a big deal. So I want you to look at Let's look at 57's kind of neat. It's about like a shot put thing. And 59. So we'll do 57 and 59. So again, all of these are odd. And if you guys, I mean, if you're having questions, you're more than welcome to email me. You're more than welcome to go to the tutoring center. I'm going to push the tutoring center again. Miss Althea is in there tutoring. It's tutoring at asumh.edu. I've had a few of you guys email me on like how to get help. Now that we've had 2 tests, you know, you kind of see where you're at. And I'm going to push her again. So Miss Althea in the tutoring center is a blessing. She knows a lot of shortcuts that I just don't have time to go over in class sometimes. So I would use her. I know if I was in this class, even if I wasn't struggling, I would get in touch with her and just to see how to have a weekly kind of session and make sure I'm on the right path. She also knows our teaching styles, which is really weird when I figured that out. Like each of us kind of have things that we emphasize more on tests, and she knows that because she's been here just as long as we have. All 3 of the math teachers. Actually, Mr. Miller's been here longer than all of us. Okay. Any questions before we end today's? Okay, I'm going to stop the live stream.